Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl from lunchboxsessions.com. Today we're going to have a look at parallel flow paths in hydraulic circuits and also the related concept called path of least resistance. It's very common for oil leaving a hydraulic pump to be split up and used on a variety of parallel branches of flow in a typical hydraulic system. What's not typical about this system is that each of our branches has only a spring-loaded check valve as the main branch load. Typically, each of these three branches would be doing something quite a bit more purposeful. You can imagine each one of the spring-loaded check valves being replaced by, say, a hydraulic motor that has different amounts of loading on it, different amount of counter torque against the motor shaft that is turning perhaps a auger feed screw or perhaps turning a winch. But now I think you could see why it's a lot easier to study the basic principles that will apply to the pressures on each of these three parallel branches if we just use spring-loaded check valves. And in this video, each of our spring-loaded check valves has a spring with different tension of wire. So the wire on the upper check valve has been wound to equivalent of 100 psi resistance. We've got a 200 psi equivalent spring, and our stiffest spring wire is down here at the bottom, 300 psi spring. We also have a couple of shutoff valves currently shown in their open position, but we'll be able to close them to block off flow paths as we need to. Now let me ask you, what pressure do you think is going to register on this gauge when we start the pump? And maybe I should also indicate that the diameter of hydraulic hose or tubing used on each of our three branches is large enough that if the entire pump's flow is passing through only one of these branches, the pipe itself adds no resistance shown on our gauge. So the spring-loaded check valves are our only resistances in each of the three branches. Shutoff valves are open. What will our system pressure be when the system is energized and the pump is turned on? If you guessed 100 psi as the correct system pressure, great, super, because that's our easiest path for oil to pass through the hydraulic circuit. If the hose is oversized and the only resistance is the spring in the spring-loaded check valve, it makes sense that the pump's flow will only move along the top parallel path, and we would only get a 100 psi system value. Now let's bring up our control panel so that we can operate our shutoff valves, and I'm going to close the top valve. What do you believe will happen to our system pressure when we close the top valve? 200 psi becomes our new system pressure because the middle branch is our new path of least resistance. Now, if we close the bottom valve, it makes sense that the system pressure will rise all the way to 300 psi because that's our only remaining path for fluid in the hydraulic circuit. What happens if I leave the 200 psi path blocked and I open the shutoff valve on the top parallel branch? Quite correct. We go back to 100 psi as the top branch becomes our path of least resistance once again. Does that lead you to believe that it's impossible for a hydraulic pump to be shared by more than one parallel branch at the same time? This simulation would certainly imply that that's the case. But if you know a variety of hydraulic systems from both plant or mobile machinery, you probably know that it is quite often possible to multi-function a hydraulic system. That is to both, say, curl the bucket on an excavator while also raising the boom, and use the same pump to achieve that. Well, how is that done exactly? Well, one way we could do that in this particular hydraulic circuit is let's leave our hydraulic tubes or hoses at the exact same diameter, but let's go and purchase a new pump. Let's go and get a much larger pump without upsizing the hydraulic hose or tubing. And let's see what happens. Watch that system pressure gauge. Interesting. Now that we're working with a much larger pump, but we kept our hose and tubing size the same, we find out the system pressure gauge is reading 279 psi, we find out that we are indeed passing flow through 2 of our 3 parallel branches. Before we analyze that further, would you say that there's the same amount of flow occurring on each of these 2 branches? You're correct if you assume that there's a little more flow passing on the 100 psi branch than there is on the 200 psi branch. But hey, at least we've managed to get flow to pass along 2 parallel branches at the same time. But where did the 79 part come from? Well, at this point, it's a bit of an arbitrary number, but it's safe to say that that 79 psi is resistance that has been added to the system pressure because we've gone to a much larger pump without upsizing the diameter of hydraulic tubing that we're using on these branches. So now it's evident that the diameter of the hoses themselves is part of the system resistance, the system pressure that we're seeing on the main gauge. Does that sound like an efficient way to get hydraulic flows to occur on more than 1 parallel branch? No, it does not. But it is common enough. It's not usually done by undersizing hoses or oversizing pumps as much as flow on 2 parallel branches may be achieved by opening directional valves on each of these 2 branches only slightly. But a directional valve that is opened only slightly on this branch and only slightly on that branch is the same thing as having undersized hydraulic hoses in the simple analysis. So how do we get the extra pressure from the hydraulic hoses to disappear? Well, why don't we go ahead and just increase our hose diameter and let's see what happens. Let's magically increase to 1 larger size of hydraulic hoses and tubing, and we find out our system pressure drops. What do you think will happen with our 2 flow paths when we move to the next size of hydraulic hose? Let's upsize once more and see what happens. Well, sure enough, we're now back to only 1 flow path. We're not yet at 100 psi, but we're at a large enough hose diameter now that it doesn't add enough pressure to the system to force flow through a second flow path. The 59 psi is simply the extra pressure added by undersized hose in the system, and so our 100 psi check valve is open, plus an additional 59 psi from undersized hoses or tubing. Let's go to the largest size, or the more properly sized hose for this particular size pump, if all we want to do is see load pressure from the check valve. And now what we find out is we're back to 100 psi, and of course flow only passing on the 1 branch. So that's a bit of an introduction to what happens when you have more than 1 parallel flow path in a hydraulic circuit and you're expecting flows to occur on more than 1 branch. But typically the path of least resistance will come into effect whenever oil can find the easiest path back to tank. It will take that route, and that will be reflected as the system pressure on our main system pressure gauge.
We have hundreds of interactive resources like this live schematic, so you can try out your wild ideas without blowing anything up. Get started at lunchboxsessions.com.